In this video, we're going to look at how to graph sine, cosine, and tangent. And then just for a moment, we're going to talk about cosecant, secant, and cotan, but we're going to cheat a little bit. We will graph all 6, but we're really only going to graph 3. We're going to start with cosine. I have all of the things that I could possibly move around in this cosine function I have here. I have a new amplitude. Amplitude is how high the cosine and the sine will go. So it's where it's going to peak and where it's going to valley. I have a vertical shift of a 3. So this whole parent function is going to move up. And then in here, you get told the omega sort of and the phase shift. And I say sort of because the notation kind of flip-flops in the textbook. You need to use the t equals for sine and cosine 2 pi over w to find what's going on here. Here's your w. And then we're going to set this whole piece on the inside equal to 0 to find the phase shift. Now my original parent function for cosine looks something like this. It starts out at the 1. At pi, it hits the -1. And at 2 pi, you're back up at the top at the +1. And halfway in between, so at pi halves and 3 pi halves, is where you're going to have your intersection points, even though it doesn't look like that on my poorly drawn graph. Let me try that again. So this would pi halves, and this is 3 pi over half. Now, it oscillates over the x-axis. We're not going to do that here. We're going to oscillate over the y equals 3 line. So I'm going to say 1, 2, 3, 4, 5, 6. And I chose 3 on each side because I have an amplitude of 3. So as I oscillate over this y equals 3 line, I'm going to hit a maximum of 6 and a minimum of 0. I also have a phase shift, so I'm not going to start here high and head down and then back up. I have to scoot everything over to the right. I know it's the right because it's a negative. First, let's talk about the period. So I'm going to take that omega, which is pi, and plug that in, and I get a period of 2. So the time I have taken 2 steps, then I will have completed a single one of these parent functions. In the time you go 2 pi steps, we'll complete 3 pi cups, so 3 and a little bit more. And it'll be a little bit more obvious than when we finish this. But we're also not going to start at the 0. I'm going to have my phase shift, and I'm going to scoot that right over here, pi over x minus 4. I'm going to set this equal to 0, and I'll get x equals 4 over pi. So this is where I'm going to start. I'm not going to start here at the 0. I'm going to start at 4 over pi. Well, I don't know what the heck 4 over pi is, so I'm going to say like this, 4 divided by pi, and I get 1.27-ish. 1, 2, 3. Actually, I'm going to just label it 1.27. And I'm going to start there, and I'm going to start high, because that's what you do with cosine. When you take 2 steps from here, so now I'm at 2.27, now I'm at 3.27, 2 steps, I'll have finished, so I'll be up here again. And the nice thing about trig functions, the only nice thing about trig functions, is that they're symmetric. So halfway in between, you'll hit your minimum. And then halfway between each of these halves, you'll intersect your line that you're oscillating around. In this case, and the parent function is the x-axis, but here it is the y equals 3 line. So halfway in between here. So if I add on a half, that would be 1.77. And if I add on a half here, that would be 2.77, where I'm going to hit. And there is my poorly drawn, super skinny cosine. Not only are they symmetric, they just repeat. So I'm basically just going to do this 2 more times since I want to see, well, 1 more time since I want to see another period. So 4.27 6.27, 5.27, 6.27. And you just say down, we hit this, and we're back up. And then this would hit just at the bottom here, and it looks something like that. So not fantastic to sketch. These things are not going to look super nice by hand. They'll look a lot nicer on Desmos, the graphing calculator that you can use online. It's very easy. You type it in just the way that you would think. So I'll just type cos, and then I have pi x minus 4 plus a 3, and I'm going to move this down so we can see, and I'll zoom out a little bit. And so here is where we're starting, and then this is where we end the first cup. Here's where we bottom out. If I put in the line that we oscillate over, you can find the intersection points, although now I lost my other points. Let me put those back up. And you can see from 0 to just over the 2 pi, right? So 2 pi would be, yeah, right about there, actually. You have this 1, 2, and now we got this piece here, which is a half. But we also have this part back here, which is a half, and a little bit extra. So about pi, right? It's about a little over 3. Rotations that we have in there, the original parent functions. You can also graph this on your calculator. It will look worse, but you can do this. 3 cos pi x minus 4 plus the 3. I'm going to hit graph. It looks pretty nice on there, just the way that it is. If you hit zoom trig, which is 7, it'll make it a little bit nicer. But you see I lose the top head. So if I do window and up my y max to a 7, and I really don't need to see all the way down to the -4, get a little bit better picture of my graph. And I can find where some of these peaks or valleys are, but you need to know a little bit about where you're going to start. So you need to know where your phase shift is. You need to know, well, I'm starting at pi divided, 4 divided by pi. So let me change this table set to ask. When I go back in the table, it will look blank, but now I can type in 4 divided by pi, and I say, oh, well, that's what it is, and that's where I start. That's how high I am. So you can get an idea of where all these pieces fit together, because many times the numbers are not going to be really nice to look at. Let's look at sine, and unfortunately we're going to look at not such a nice one, because this sine is not set up for us yet. They gave us the information and they said, hey, figure out what the equation is so that you can graph it. Amplitude's easy. We know that goes here. I don't have a vertical shift, so that's like a 0. So I don't need to write +0. I could just go ahead and leave that blank. This is the messy part, the period and the phase shift. And it's messy because it's not really clear in the textbook that the way that they have changed these things. So they gave me the period. So what I'm going to need to do is use that to find out the omega. Usually they give you the omega, right, and you find the period. Here they said, hey, period, the t is 5 pi. What omega would be inside of the trig function? What's the frequency? How many rotations are you going to complete in 2 pi steps? So I'm going to need to cross multiply and divide. And you can see that omega is 2/5. So basically you would have to go when you go 2 pi, you only get through 40%. Here's the other thing. So we know that goes, well, we think we know, right, that it goes here. And then it says, oh, phase shift, 1/8. Okay, so that's positive, so it needs to be negative in here, right? This just seems like a reasonable thing to do. However, if you check this, I need my phase shift to be 1/8. right? So I need to verify that this is what's going on. If I do this, do I start at an eighth? No, you can see this right away. Because when you add this over, you get 2/8, that's a fourth. And when you multiply both sides by the 5/2, your x is going to be 5/8. Well, 5/8 is not 1/8. So what happened? What happened is what they really gave you when they told you the phase shift was this. And that happens a lot when you're building the equation from the information. What we really need to have is 2/5 x minus, well, I can leave it as 2/40, or I can reduce that to 1/20 in there. And that's going to give me a phase shift of an eighth, right? So if I set this equal to 0, then I'll get out the eighth. So that is definitely a little sneaky, because the two numbers you see here doesn't look anything like what you see had I given you the equation and said graph me. The nice side of it, though, is if you have the phase shift already, you kind of already know where to start. You can, if you're comfortable graphing and I tell you these three things, you really don't need to build the equation anymore. Let's start talking about how to graph this thing. My parent function for sine looks like this. Starts off at 0, hits a maximum at 1 at pi/2, crosses again the x-axis at pi, minimum at a -1 at 3 pi/2, and then we lock it all up at the 2 pi. So symmetric again. I have two halves, and then halfway between each half, right, the first quarter and the back quarter, you're going to hit your peak and your valley. Now, I'm still going to be oscillating over the x-axis like in the parent function, since I don't have a vertical shift, so that makes life a little bit easier to graph. It's going to be much taller, so it's going to peak at a 7 and valley at a -7. I also have this phase shift, and it's going to take a really long time to finish one, right? Remember that it was 5 pi, so this finished 1s and 2 pi. I need to go all the way out to 5 pi to do this, so this is going to be stretched out and much higher. I'm going to graph it this way. Since I have a period of 5 pi, I'm just going to label these pi. There's no rule that says you got to label it 1, 2, 3, 4. You can label it whatever you want. Have each interval, like the step in between, be a +1, like we had before, 1.27, 2.27. That's probably going to make your life easier. All right, so my phase shift is at an 1/8. So I'm not starting at 0. I'm starting at an eighth, which is a real pain. And then I need to go 5 pi steps to finish one, but that's not at 5 pi, it's at 5 pi plus an eighth, right? That's how I go 5 pi steps. If I stop at 5 pi, I'm a little short. Halfway in between, I'm going to intersect. So I need to find out what that midpoint is of that section. So I have 5 pi plus an eighth, right? Plus another eighth. And then I say divide by 2. So at like 7 point, just about 8. The other thing you could do is, if you know half of 5, of course, is 2.5, you can say, well, how about 2.5 pi plus an eighth? That works too. And that's where I'll intersect. Halfway between this first half, I'll hit the 7, and then halfway through the back half, I'll hit the -7. So you can do this again with your midpoint. You can just play with it a little bit. If it says sketch and you don't need it to be exact, that's fine too. An eighth plus an eighth is a quarter, so I'm just going to go ahead and write it like that. Say divide by 2, so like 4.05-ish. So that's a 3 and that's a 6, so like what, right about there-ish. And then I'm going to have the same thing here. 5 and 2.5 is 7.5 pi plus the quarter. right? Just add those two numbers, two weird numbers together, 2.5 pi plus an eighth and 5.5 pi plus an eighth. And divide by 2. Just about before 12, which would be right about here-ish. And actually, it should be up here, right? 7. And then this one be down here at the -7. And here, it's a terrible, terrible sine curve. Oh, well, actually, this curve itself came out pretty nice. Terrible numbers. Let's look at it at Desmos, if I can even remember. So I'm going to change this to a 7. I'm going to make this cosine into a sine. And let's see, I could write it either way. I'll say 2/5 x, and then in here I'll put in that 1/8 that they gave me. Close that up. I did not have that, so I'll take that 3 out, and I don't need that right now. And there is the function. It's really, really big, so I'll make it smaller. Let's see, there's the 1/8. 5 pi plus an 1/8. In between, remember that number from before, just before the 1/8? There's your 4. And then it should be these, let me think about this. It should be this number plus the 4, right? Yeah. And there's your function. Again, terrible numbers. You can graph this in your calculator the same way. I would distribute, though, because you'll have a lot of parentheses in the calculator otherwise. Now for my nemesis, tangent. We are not friends. I don't like tangent. I don't like tangent because its parent function is all wacky. Tangent's parent function looks like this. It has an asymptote at the even pi over 2. So my parent function will have an asymptote at pi over 2. And it doesn't even start at 0. So rude, right? It goes from negative pi over 2 to positive pi over 2. And the fact that it has the asymptotes and it crosses at the 0 kind of throws off an amplitude. Now, you're still going to have an amplitude given, but it's kind of a fake amplitude. And what we're going to use to stretch or shrink our tangent is going to be at the pi over 4, where that equals to 1. And what's going to happen is, as this squeezes together, the pi over 4 is going to hit a much higher number. And if it squeezes out, the pi over 4 is going to hit a lower number. So you're not locking in the 1, you're locking in what is going on at pi over 4. So you can plug in pi over 4 and see what you get, or you can remember the rule that it's going to be halfway between this, and then of course halfway between this. That's going to move your 1 and your -1. All right, so I got an amplitude of a 3. I don't have a vertical shift, so that makes life a little bit easier. With the tangents, I actually start with the phase shift, and I don't phase shift the 0. I phase shift the asymptotes, because then I know where it essentially ends and begins, and I can start chopping this up into quarters like I did with sine and cosine. So my period for tangent, its parent function is only pi, right? Negative pi halves to positive pi halves. So it's pi, not 2 pi. Divided by my omega, well, here, that's a 3. So this is going to be very fast. You're going to travel pi over 3 steps, and you're going to finish one of these tangent squiggles. Okay? The phase shift is going to start, instead of in here, it's going to wind up being over here, but I'm going to use these asymptotes to kind of lock it in. So instead of setting this equal to 0, I'm going to set each one of the asymptotes equal to what's on the inside from the parent function. If I add over pi, well, 1 pi is like 2 over 2, right? So 2 pi over 2. I would have 2 pi over 2 plus a negative pi over 2. That's going to leave me with a positive pi over 2. And when I multiply by a third, I get pi over 6. So this one is going to get scooted over this way to pi over 6. Let's solve this side. There's my 2 pi over 2 again. I add it over. Now I have 3 pi over 2. When I divide by 3, I'm going to get pi over 2. And actually, this one is going to wind up staying. So it's kind of like this. This one gets squished in all the way like this. Interesting. Okay. Let's start graphing. Let's see. There's my y-axis. And I have pi over 6 and pi over 2. I can write that as 3 pi over 6, right? So that way I can label these with steps of 6. So I have pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Not that we need that one. And I have an asymptote here. Boop, 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 boop. And an asymptote here, right? That's at pi halves. Tangent is still kind of symmetric, right? So halfway in between is where you're going to cross. And halfway in between the first part and halfway between the second part, and actually the first part's down here this time, is where you're going to hit the grabber, the amplitude. So at, let's see, this is what? 0.5, oh, this would be, yeah, 1.5 over 6, 1.5 pi over 6. You'll hit the -3. And at 2.5 pi over 6, you'll hit the +3. Not pretty, but there he is. And then, of course, it's going to right up along those asymptotes, and then we have something that looks like this. Let's look at Desmos. I have a 3 here. This turns into tangent. And I had 3x minus pi. Ooh. Ooh. Oh my goodness, look how fast it is. All right, let's get in here, because this is the one that we, oh, you can even kind of see it. Here we are. All right, so there is the pi over 3 0, right? So that's where we started. And now it's not going to do the asymptotes as nicely. Let me see if I can get those. You can kind of see them, but it doesn't make them, you know, dotted or anything like that. So I'm just going to go ahead and leave that out. Now let's talk about our grabbers. That was at 3 and at -3. Okay, so we have a lot in there. There's the pi over 3. Here's 1 down at the -3. Oh, but that doesn't look like 1.5 pi over 6, or does it? I'm going to ignore the pi for a minute. 1.5 divided by 6, that's a quarter. It's really kind of a bad practice to put decimals in your fractions. I do it because I'm lazy, but they really don't belong in there. And then, so here's my other one. Wait, I think, am I in the right spot? Nope, there he is. 5 pi over 12, right? Because the other one was 2.5 divided by 6, and that is the same as 5 pi over 12. So there they are. And look how squished up he is. He almost looks like a straight line, right, if you go further out. Ugh, it's kind of crazy looking. Okay. Now, what if you have to graph secant or cosecant or tangent, cotangent? Terrible. Well, sort of. I'm going to go back to this cosine. I'm going to erase all of this. And what if it said, no, 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 graph secant? Well, what you do is you don't graph secant. You graph cosine. And then at the peaks and the valleys, you put your little parabola looking guys. And where you're going through the translated roots, right? So that would be here. Those become asymptotes. And you do that for sine and for cosine. So you do that for secant and cosecant. I'm going to pull the cosecant, the cosine one back up. I believe that was it. All right, and they said, well, what if they actually said, no, I want you to graph cosecant or secant? Watch this. If I can get it. Oh, there he is. See? So you can just graph the cosine one and then take all of those and draw it out. Now the asymptotes aren't on there, but you know where the split is because you know how cosine works, so that you know that you're going to have at this point right here, I don't know if I'm going to be able, this may not graph particularly nicely, that's where your asymptote is. I'm kind of rounding out so it looks a little bit closer than maybe it should. And you would do that if it said graph cosecant, then you would just graph sine and do the same exact thing. Let's look at tangent and cotangent. So we'll pull up our skinny little tan function that we had just a moment ago. 3x minus pi. Right, I'm gonna blow it in a little bit so it's not too hard to see. Now let's look at cotan. And look at that. So where the asymptote is, that becomes the root, if you will, the solution where you go through wherever it was before. And then it grabs in the same spot. And then the point where you were at for the, let me turn this one off for a second and turn some of these on so that we can get a better idea of which one we're looking at, because I know it's hard to see. Right, so we had this one, and this one, right? And then my asymptote was at pi over 6 and pi halves. Let me turn the cotan back on. And you see how I have that same one this way, but it backs up to the one before it. And then here is that pi over 6. So the asymptote, so it goes backwards. It's like it spins. And so the other one that was here is actually going to be the other part for this way. So it's like you take this and spin it over to where the other one is. So it's pretty nice. So you don't have to graph them all over again. Of course, tan and cotan, they're not as nice as sine and cosine and that relationship that it has with cosecant and secant. But you can work your way backwards from the tangent without having to remember how to use cotan. I apologize for the long video, but now you know how to graph all 6 trig functions.